Okay, this video is going to be on acceleration, and to put it simply, acceleration is the rate of change of an object's velocity. How fast do you change your velocity? So like 0 to 60 in 2.2 seconds would be an acceleration. Okay, so up until now we've talked about objects going at a constant speed. Okay, we've looked at what's called a uniform motion. Most things, as you know, don't go in a straight line at a constant speed. Now let's look at these motion diagrams that we've been dealing with for the last couple weeks. So A, not moving. B, you should say, okay, there's equal spacing between all these. They're going at a constant rate, a constant speed. This one, the gaps are increasing. You're increasing speed. D, the gaps are decreasing over time, so they're slowing down or going at decreasing their speed. Okay. All right. So hopefully you can do this now. All right. So when we look at the major indicators for change in velocity, we can look at the dots, and we need to look at the vector diagram, the vector arrows that are drawn between the dots. Okay, so like for the one on the left here, the stick figure person is moving left to right, but the vectors, the arrows, are getting progressively bigger. Okay, so as it speeds up, the arrows get bigger. This one, they're slowing down. The arrows are getting smaller, but they're going in that direction of motion. All right. So again, if an object speeds up, the vectors get longer. If they slow down, the vectors get shorter. Okay, so we have a rate of change of speed here. We could see here that we have a positive change in velocity. Here we have a negative change in velocity. Okay. All right. So we can't really know everything from looking at the motion diagram. We have to draw we have to look at a graph, or we have to look at more data points. But the rate that the velocity changes is acceleration. All right. So we can look at this motion diagram and actually figure out the acceleration from it. So if we look at how our velocity changes here from this dot to the end of box one, we really get that we have two different velocities, two different arrows. So the acceleration then would be the difference of these two arrows. Okay, so our acceleration is to the right, the difference of the VF minus the VI. Okay, which is also equal to the change in these vectors divided by the time from here to here. All right, so again, you can determine the length of an acceleration vector by subtracting the two consecutive velocity vectors and dividing it by the time. Okay, it looks like this. Change in velocity, which is acceleration, is v final minus v initial over time. Okay. So acceleration is change in velocity over time. All right. So in this case, our time interval was 1 second from here to here. So the average acceleration or time interval is this a. So when you're making motion diagrams, you can actually figure out, if you look at the velocity dots or the velocity vectors from your position versus time graph. If you know the time intervals, you can figure out the acceleration of that object. All right, so now the thing, we know that it's changing in velocity, but the acceleration has a direction too. It is also a vector quantity. All right, so this is big. When the acceleration is in the same direction, the object speeds up. So when acceleration and velocity vectors are in the same direction, you have an increase in speed. And when they're in opposite directions, the object is decreasing speed. Because the acceleration goes in the opposite direction of motion, it's slowing down. It's taking away velocity. Okay, so there's really four ways that you can draw acceleration and velocity on a distance versus time, or on a position diagram here. So this first one, they're spreading out. So we get a bigger velocity as we go. Okay, so VF is bigger than VI, so acceleration is going in the same direction as the motion. The second motion here, the dots are getting closer together, the object's slowing down. So VF is actually shorter than VI, so acceleration is in the opposite direction because it's slowing down. Okay. Then you have it where we begin here, so we're speeding up the other direction. So acceleration is going in the opposite direction. Okay, we're going, the car is moving left. Our acceleration is left. And then this one, our acceleration is slowing down to the left, so our acceleration is to the right. Okay, these are the 4 ways that you can have arrows for acceleration and velocity. They're either the same directions, like the first one and the third one, or they're in opposite directions. If they're in the same directions, they're speeding up. If they're up in opposite directions, they're slowing down. Okay, and then again, object to have a positive acceleration when the acceleration vector points in the positive direction, and negative when it goes in the negative direction. Okay, again, it does not always indicate whether the object is speeding up or slowing down. It just indicates which way is the acceleration happening. All right, so we've been doing a lot of stuff with position versus time graphs, or position versus time, and we're going to do some velocity versus time graphs, but they all come from these motion diagrams. All right, so again, acceleration is a change in velocity in a given time interval. Its unit is meters per second squared, because it's how fast you change velocity. So if velocity is meters per second, the rate of change is another second, so it's meters per second, or meters per second squared. Okay, so we have this graph on the right here. So if you look, we are changing velocity over time. We're increasing velocity over time. So therefore, we have an acceleration. We have a rate of change of velocity over time. And if you have a velocity versus time graph, the slope of it is your acceleration. If you want to think of it in terms of units, meters per second, rise over run gets you your acceleration. Okay, so just kind of some interesting things to look at here. If your velocity, now look, we're having a velocity versus time graph. Our velocity increases, you have a positive acceleration. Velocity remains constant, there's 0 acceleration. Velocity decreases or becomes more negative, we have a negative acceleration. Okay, so let's look at this thing for a moment. To describe, how would you describe the sprinter's velocity and acceleration on this graph? Well, you could say that the velocity is constantly increasing, and you'd be right. But if we look at the acceleration, the slope of this, okay, at this first part, yes, there's positive acceleration. Then the acceleration decreases here to almost not a whole lot of very minimal acceleration right here. You got to take the differences of the slope. So a lot of acceleration, not a whole lot of smaller acceleration, and then very little acceleration right here. And we could take the slope of each of these parts of these lines and figure out what the acceleration of that line is. Okay. Now, we talked about rate of change in velocity is acceleration. This line is important. Acceleration can occur when speed is constant. When we look at something in orbit, the speed is constant. However, because it can undergo a constant acceleration, it's changing direction at a constant rate. Because remember, velocity is speed in a given direction. Okay, so if you're constantly changing direction in a given rate, then you are having a constant acceleration. So because it's changing direction, its velocity is changing, and therefore its velocity is changing, there is an acceleration. All right, next part. All right, so for an object with a constant acceleration, the relationships between position, velocity, and acceleration can be described by graphs and equations. This is where we get some of the math equations, and we're going to look back at some of the graphs too. All right, you should be able to answer these by the end of this video. All right, so we start with our data, like you've done in class. Position versus time data. Okay. And then we can plot this on a graph for position versus time. And it looks like this. This expression here is your data. Okay. And then we have different slopes to get different times because the graph initially wasn't constant. Okay. So because we have a curve in position, we're going to have a change in velocity, which means we're going to have an acceleration. Okay. And this one's important. For an object with a constant acceleration, the position versus time graph is a parabola. It's a curved position time graph. All right. So if we take our velocities from the previous graph, like you've done in class, then we make a velocity versus time graph. Okay. Now with this one we've done, when you do this, you notice that the velocities make a straight line. Okay, what this means is that we have a constant acceleration. Just like when you had a straight line like this for position time, we had a constant velocity. In this case, because our velocities are increasing, we're constantly speeding up. We had that nice parabolic graph for the position versus time. We're going to end up with a constant acceleration here because our slope of our velocity versus time is a constant slope. Okay. Now, so unique position time graph can't be created from a velocity versus time graph because we don't know where it starts. We don't know where the positions are. We can't take anything from the velocity versus time graph for where it was on a position. But we can figure out how far it travels. Okay, so we know that the velocity is change in position over time. So if we rearrange this equation, position then, if we isolate the delta x, it's just v times t. So speed times time gets us our displacement or how far it travels. Now on a graph, v is our velocity, t is our time, so the area under the curve will give us what our object's displacement was. Now next to how far it traveled, but the displacement, how far it was from where it started. Okay, so in this case, if we're looking for from times 1 to 3, the object's traveling at 8 meters per second. So we would take our velocity of 8 times our time of 3 to get 8, or excuse me, time of 2. We're only looking from 1 to 3 seconds. So 8 times 2 is 16. So this object would have a displacement of 16 meters. Another way to think about it is we can take meters per second times seconds. And when we do that, our seconds cancel out and we're left with a unit of meters, which is the area unit. Okay, so if an object's average acceleration is, if we know it, we can use that to determine how much velocity changes over time. So there's your equation. Initial equation, acceleration is change in speed over time. And we can write it like this. We're going to solve for v, multiply both sides by t, and we get change in speed is acceleration times time. All right, so we can write it like this, because vf minus vi is equal to at, as in the previous equation. And then, so this is another one if we're looking for final speed and we know our initial speed, take acceleration times time, add our initial speed to it, and we get our final speed. All right. A lot of these are going to deal with constant accelerations. Okay, and then we can find the final velocity using the graphs. Okay, it can also be used to calculate the initial velocity of an object when they both at the time. Okay, So we have a velocity versus time graph here. Now notice, this has a constant velocity. So in your head you should think, okay, constant velocity, zero acceleration. However, we're going to find the displacement from t equals 1 second, or at t equals 1 second and t equals 2 seconds. To do this, we know our velocity, and we're looking, so the displacement is the area under the curve. So at 1 second, we're looking for where it says delta t, this initial delta t. So velocity is 75. So 75 is the height. The base of it is 1. So 75 times 1 is 75 meters. Now at 2 seconds, the base is 2 seconds. The height is still 75. So 75 times 2 is 150. All right, so now this one we have an acceleration. So for this, we'll have to look at figuring out the area under this entire curve. Well, we have a rectangle, but we can also break this upper part into a triangle, and the area of a triangle is 1/2 base times height. So to find this whole thing, we would take the area of this rectangle, which is just the base times the height, to find this bottom rectangle. To find the area of the triangle here, because it's a right triangle, it's 1/2 base times height. So 1/2 the base times the height. Okay. So like that. And because we know, so substituting for the change in velocity in the equation gives us, so because we have change in velocity, because this change in velocity is for that triangle now, and change in velocity is acceleration. Acceleration times time is change in speed from the previous equations. We get this. Okay, these will be given to you on an exam, but you will get some practice using them. All right, so when we know the initial or final position of the object, we can write it with this. Okay, we will be doing some practice with this in class. All right, so if we have an initial time of 0, we don't need to worry about the initial time. We can just throw in this equation. A lot of times it's written like this or like this. But if we want to solve for v final, and we know how far it travels, we can use this derivation of the equation as well. Okay. So here are the equations. I would definitely know these. Look at those, make sure you understand how to do them. Okay, the last part of this constant acceleration is an idea of free fall. And free fall is simply when an object is accelerating only due to gravity. Okay? And because it's accelerating due to gravity, all the kinematics equations that were shown earlier apply. So free fall is the motion of an object when gravity is the only force acting on it. Okay? And what Galileo actually found was that free fall acts pretty much uniformly on all objects of the same shape. So if you take a baseball and a bowling ball and you drop from the same height, they're going to hit the ground at the same time. Because gravity is the only thing pulling them down. It's the only thing causing them to accelerate. Gravity is the only thing causing them to accelerate downward. Okay, and he found out that the objects accelerate downward at what's called the acceleration due to gravity, which is 9.8 meters per second squared down. Okay. And the signs do matter. Okay, so we have a ball. We start here and we throw it. We release it with an initial velocity of 20 meters per second, like shown here. And when you throw it upwards, it slows down when it gets to the top. Its displacement looks like this. So it starts at a certain height and goes up a little bit higher. Okay, but its velocity decreases. Now, if we look at this velocity time graph, because it's a straight line going downward, it has a constant acceleration of actually negative 9.8. All right, at the top of the ball's flight, the ball's velocity is 0 meters per second. What would happen if its acceleration were also 0? So think about that. If its velocity was 0 and it wasn't changing speed, hopefully you could see that it would just sit there and not do anything. Okay, the ball would not gain any downward velocity, it would simply hover in the air. That's not what happens. It goes to the top, kind of sits there for a brief second and comes back down. Okay, there has to be a downward acceleration. There's been some changes. And again, obviously, you can look at the factors that affect the value of free fall. The greater distance, you have a little less acceleration, and we're going to talk more about that later on. Okay, but again, most of it deals with these equations. Now, when we're talking about free fall, acceleration is constant. So if I know, for instance, if I have this object dropped, and if I know this equation right here, and let's say I drop an object from rest, so I just let it go, I let it fall down, and I know that it's going to fall, let's say it falls 2 meters, okay? So I would take 2, acceleration due to gravity is 9.8, I'm going to make that close to 10. So 2 times 10 is 20, times 2 is 40, and we take the square root of that to get our final speed. Okay. You're going to have lots of time, you're going to have lots of math practice, okay? But I do want you to look through these equations, snap them, and notice where it says no T, no D, no V final, no T's. When you're looking at what equations to use in your problems, and you come to this, you say, okay, what don't I have? And if you don't have something, you know what you can eliminate. So if you don't have a T, you're going to look at the top one or the fourth one. Okay. And that is the end of this little video. Okay. Go back and look at the problems, answer the questions on the formative, and we will talk to you soon.